Let's delve into cosmic mining, the ultimate horizon for gathering resources. Every mineral, metal, and element we might ever require to sustain an infinite human society until our sun meets its end exists within our stellar vicinity. It was Neil deGrasse Tyson who predicted that asteroid mining might create humanity's first trillionaire. Yet it's not merely about vast fortunes. The challenge lies in harvesting these materials and then deploying them wisely. This journey will be immensely challenging, exorbitantly costly, and not without its perils. However, space extraction is fundamental to fostering interplanetary human existence, and in the process, might just be the key to preserving our home planet. It's far from a straightforward gold rush. The complexities are monumental. How then do we navigate this? Is the venture justified? And once we extract these off-world treasures, what next? Subscribe to the channel and let's explore. You are watching Adventures in Space. Today, we'll delve into the trio of cosmic mining: asteroids, our moon, and other celestial bodies, particularly Mars. We'll initiate our discussion with asteroids, as they promise immense benefits, but are equally complex in their nature. Asteroids intrigue us because they represent the untouched remnants from eons ago during the inception of our solar system. All the metals, rocks, and gases that couldn't culminate into planets transformed into asteroids. This means asteroids are composed of planetary ingredients but are more condensed and easier to access. When planets take shape, extreme heat causes their composition to turn liquid, leading heavy metals to gravitate downwards, and the densest ones forming the nucleus. This concentrated core produces gravitational force, attracting more materials, thereby shaping the planet. However, many asteroids sidestepped this melting phase, leaving behind huge clumps of dense metals floating in space. These are particularly appealing for their resource-rich profile. M-type asteroids, for instance, typically consist of 80% iron and 20% of a blend of nickel, iridium, palladium, platinum, gold, magnesium, and other valuable metals like osmium, ruthenium, and rhodium. Some of these asteroids possess more nickel than all of Earth's known reserves combined. Even more captivating is the abundance of rare metals like platinum, palladium, and rhodium on these space rocks. These metals, pivotal for products like catalytic converters in gasoline vehicles, have gained significant value on Earth, causing them to become sought-after commodities, sometimes even leading to theft. While these rare Earth metals aren't exactly scarce on our planet, they are dispersed, making them elusive. Unlike gold that forms large deposits, these metals are spread thin. Yet, on a metallic asteroid, a single chunk several hundred meters wide could potentially offer more platinum than has been or will ever be extracted on Earth. Imagine the prospects if we could harness all desired metals from asteroids, sparing Earth from exhaustive mining and looking to space instead. The vast expanse of space offers a plethora of untapped resources. To access them is where the challenge arises. While every asteroid is an object of intrigue, not all possess the wealth we seek. Studying them can reveal groundbreaking scientific insights, but for mining, they vary in richness. A preliminary scouting mission becomes paramount to confirm the asteroid's contents before making any decisions. Much of our understanding in planetary science relies on present-day data, which can be refined or debunked tomorrow. Even if we identify a treasure trove, getting to these celestial bodies isn't straightforward. Many sought-after M-class asteroids are nestled between Mars and Jupiter, in the heart of the main belt. Although this isn't a significant distance on a cosmic scale, for humans, it's considerably beyond our usual reach. We've successfully dispatched sizable probes deep into the cosmos and even landed vehicles on Mars. However, asteroids are a distinct challenge. Engaging with planets like Jupiter allows probes to harness the planet's gravitational pull, achieving stable orbits. Landing on planets like Mars or Venus lets us utilize their atmospheres to decelerate. Such tactics are ineffective with asteroids. They might possess a gravitational pull, occasionally even boasting a moon, but these forces are feeble. Approaching an asteroid without overshooting it, and subsequently ensuring a gentle landing demands sophisticated solutions. Propulsion is a potential method, but it consumes vast amounts of fuel. If the intent is to extract metals from an asteroid and return with a significant haul, the fuel requirement becomes enormous. Moreover, cinematic portrayals of asteroid landings, like Bruce Willis's portrayal, are far from reality. Asteroids, more often than not, are analogous to airborne gravel, held together by minimal gravitational pull. As they journey through space, they gather an array of particles, akin to cosmic vacuum cleaners. The optimal scenario for landing is akin to settling on a gravel mound. In a less favorable situation, the landing module might sink, much like in quicksand. Assuming a successful landing, the extraction process remains a puzzle. On Earth, blasting rock formations is a standard approach to unearth minerals. Such an approach is unfeasible on asteroids, as the debris would scatter into the void. A meticulous and innovative approach is essential to pinpoint and extract these space-borne resources. Crafting such a method remains a task ahead. Mining on bodies like our moon offers practical advantages over asteroids, despite the lunar surface not being as resource-rich. However, there's still significant bounty on the moon. Historically, the moon experienced volcanic activity, causing heavy metals to rise and solidify on its surface. This has resulted in abundant deposits of iron and titanium. Intriguingly, moon rocks contain a concentration of titanium that's approximately 10-fold greater than similar Earth rocks. The reasons for this disparity remain unclear. Yet, the presence of these metals can significantly aid future lunar infrastructure development. Moreover, the absence of a lunar atmosphere means countless asteroids have impacted its surface over eons, making craters treasure troves of valuable materials. Furthermore, the moon is a reservoir of helium, a resource currently dwindling on Earth. Helium's inert properties make it invaluable in preventing corrosion and combustion. It's pivotal in manufacturing fiber optics, semiconductors, hard drives, microscopes, airbags, and cell phones. Notably, liquid helium plays a crucial role in cooling MRI machines. The moon's surface also houses an abundance of helium-3, a rare isotope on Earth but common on the moon due to increased solar-wind interactions. If scientists unlock the secret of nuclear fusion, helium-3 could potentially fuel our planet many times over. Extracting resources from the moon brings a unique set of challenges, with lunar dust at the forefront. On our planet, erosion shapes and softens the rough textures of rocks and granules. This gives us the pleasant sensation of sand between our toes. However, moon dust is essentially the antithesis of our serene beach sands. It's abrasive, coarse, and sharp. The Apollo astronauts had a brief yet challenging encounter with it. The dust damaged their equipment, marred visors, hampered machinery, and clung so stubbornly that they inadvertently carried it into their module, leading to respiratory discomfort. Apollo 17's commander, Gene Cernan, emphasized lunar dust as perhaps the most significant barrier to moon missions, even suggesting its potential insurmountability. Imagine the billowing clouds of dust created by mining activities. Due to the moon's minimal gravity and absent atmosphere, the dust won't simply settle or drift away. Instead, it may hover over the terrain indefinitely. In essence, continuous lunar activities might generate a perpetual haze of dust encircling the moon, a disastrous scenario. Switching gears to Mars, it's already renowned for its colossal natural dust tempests, so our activities might be less impactful there. Moreover, our past missions, including landing sizable apparatus like the Perseverance rover, akin in dimensions to a Honda Civic, have proven successful. Like the moon, our gaze is fixed on Mars's volcanic regions, which promise rich deposits of coveted metals brought to the surface by volcanic activities. One such noteworthy structure is Olympus Mons, a monumental volcano and the solar system's highest mountain. Its towering presence on Mars's landscape is attributed to the planet's lack of plate tectonics, causing it to erupt at the same spot for eons. Several similar volcanic zones on Mars beckon with the allure of precious mineral wealth. Mining on Mars stands out as perhaps the most economically feasible and crucial among the concepts we've discussed. If we envision humans inhabiting or undertaking extended missions on Mars, they must be self-sufficient, drawing resources from the Martian environment. Launching payloads into low Earth orbit is challenging and costly. Transferring them to the moon intensifies these challenges, and transporting them to Mars and ensuring a safe landing is an even more daunting task. Continually supplying Martian settlers with Earth-shipped resources isn't a sustainable approach. Therefore, extracting vital elements like water and oxygen becomes imperative for their survival. Furthermore, sourcing hydrogen and carbon will be pivotal for future rocket fuel production. Metals like iron, nickel, copper, gold, and titanium, typically found in volcanic areas, will be instrumental in building Mars's infrastructure and advancing its technology. The complexity of these endeavors cannot be understated, demanding a collective effort from Earth's inhabitants. The sheer magnitude of this undertaking is beyond the capacity of any single company, country, or space agency. It will indeed be riveting to observe the unfolding of these ambitious plans in the coming decades. But what do you guys think? Space mining. Is it bogus or the key to unlimited wealth? Drop your theories in the comments section down below. Come back here for more updates on everything space exploration related and much more. As always, this was Georgie with Adventures in Space, and I will see you in the next one.